All righty. Hello, everyone. Just make sure that this is recording. Looks like it. Okay. Yep. All right. So I'm going to do a little exam review. I wish, I have taken a couple classes from Dr. Johnson. I know some of you wanted maybe some more info on like how the exam is run, kind of what to expect. And honestly, I've never had this exam format. This is a new thing, so I can't really tell you how the multiple choice stuff is going to go. I know in the past it's been, 4 questions, 3 hours, open book, open notes. So I know that the multiple choice is also open book, open notes, but I'm not familiar if you have some sort of time limit or exactly what to expect. But expect, you've had some like the SHP problems, not necessarily the book problems, but the SHP problems. Those are generally pretty representative of the kind of level of questions that Dr. Jones asks on the test. I do know that he is willing to give you lots of partial credit if you can prove that you are mastering course outcomes and you go and talk to him after if you don't get the score you like. So, but that's about all I know. So I'm just going to kind of jump into the review here. So what I decided to do for the review is I'm just going to go through maybe big concepts from all the chapters and stuff. And I know Dr. Jones he's probably talked about a concept map in class. So I am essentially going to go through all the major concepts and make a concept map or a mind map to see how maybe I organize it, and then you guys can kind of get your own ideas from that and do something that works for you. This video, might be a little long since I'm kind of going to be drawing this on the fly, and so feel free to speed up the video. Okay, so what I would do is just switch this to tablet mode real quick. Okay. All right, so what I would do is I would start off my concept map, right? And I might put thermodynamics here. Just make sure my settings are good. Okay. So I might put thermodynamics here, right? And then I would, I might say laws right here. Right? And so what are the laws of thermodynamics? Okay, so first off, this is not necessarily a law of thermodynamics, but I would say it's a law for Dr. Jones' class, right? So, and this law is going to be choose a system, draw interactions with surroundings, and then use basic concepts and fundamental laws. I'm sure he said this a lot in class. This problem solving approach that you go through of these 3 steps, you want to follow it like it's a law. Okay, fundamental laws. You want to follow this, like it's a law. So when you're uploading your work and stuff, do not upload any work without a dashed line, choosing your system, and some arrows crossing the boundary describing the different interactions. It is a huge mistake if you think you can get through this class and through Dr. Jones' questions without doing that. Because immediately what that shows a majority of the time is that you don't actually know what you're doing. Okay, and you're not going to be able to earn as many points if you do that. So please, 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 beg of you, choose a system, draw the dashed line, draw the arrows across the dashed line, and then use your laws and concepts, right? And I promise you, if you do that, and you will be able to argue more points from Dr. Jones than the other way. Okay, so we go, we have the 0th law of thermodynamics. This one is not talked about quite as much because it's just common sense, right? Like, essentially you say 2 objects touching will become in, well, thermal equilibrium, right? So that's like you have block A, you have block B, right? And this one might be 100 degrees C, and this one might be 80 degrees C. And then you put A and B together, and assuming they're the same mass and same material and everything, then maybe you get this to be 90 degrees C, right? So that's just a common sense one. You put the thermometer under your tongue, right? And the thermometer is going to be the same temperature as your tongue. All right, so that one's just a common sense one. Then we have like the first law, which is energy, right? So this says that actually what I want to do is say E energy is equal to the sum, right? And you think of all the ways that energy is here. We have internal energy, we have potential energies, we have kinetic energies. There's possible other energies, magnetic and stuff, right? But we don't really worry about those. Okay. And then we can take a time rate of this. Okay, so we can say if system, so we go time rate, right? We get dE dt is equal to du dt plus d, and change in potential energy dt plus dke dt plus other things, right? So here I would say in 321, these equal 0. Okay. And then since these are time rates, we can say 0 if PE and KE of whole system do not change, right? And so from there, we get that dE is equal to dt. Sorry, dE over dt is equal to du over dt. And from there, we say, how can change U? So this is through heat and work, right? Thus, du dt is equal to the summation of heat minus the summation of work. There should be a time rate there. And we can also change it through mass, right? Plus m dot n hi plus vi squared over 2 plus gzi minus m dot e he plus ve squared over 2 plus gze. Okay. So these terms equal 0 for closed system because there is no mass flow. And then you could also say if open system, generally changes in potential energy and kinetic energy are negligible. Unless other context in problem is given. Okay, so that's kind of the stuff for the first law, right? So that, I kind of went through a derivation. Maybe in your equation sheet, you don't need all these different steps, but this is to show you, you write down this equation a lot, du dt is equal to the sum of the work minus the sum of the heat minus the sum of the work, plus, any changes in mass flow and the thermodynamic properties associated with the mass flow. So that is where the equation comes from, and those are the assumptions, the underlying assumptions, right? And so then, the next thing you might say is, okay, so we want to look at second law, right? And so the second law, right, we have the ds, the change in entropy, is equal to the sum of the heat interactions with the boundary temperature plus m dot I SI minus m dot E SE plus S dot gen, right? And then here you can put the assumptions, for closed system, m dot is 0. For internally reversible system, S dot gen is equal to 0, right? Okay. All right, so let's see, what else do I have on my list? So, okay, so as a subset to this, right, I might have statements here. Oops. Right, so these statements are, they're essentially, I would say, they're part of laws, they're things that cannot be violated, right? So you have Kelvin Planck, and you also have Clausius. Okay, so Kelvin Planck, right, is essentially you have to reject heat, right? So, for example, on that the example problem that I showed in the practice exam, right? That system will never work because if you look at it, it receives heat, but it never rejects any heat. So that violates the Kelvin Planck statement. Okay. So the Clausius statement is you have to plug in the refrigerator, right? So you can't move energy from a low temperature body to a high temperature body without putting work into the system. So in this case, you'd have to plug in the refrigerator, right? Okay, so yeah, and then you might put page numbers here if you're interested in the full definition. Okay, then something I want to come back to here is this work term, right? I think the mass flow is pretty easy to understand. You can tell if mass is crossing the boundary, right? But how do we decide what work interactions to include? Okay, so for 321, we worry about boundary work. We worry about electricity crossing the boundary. And we worry about shafts crossing the boundary. Okay, so this is one reason why it's so important to have your schematic and your dotted lines, right? Because all three of these have to do with the dotted line, right? Well, at least the crossing of a dotted line. Sorry, these have to do with the crossing of a dotted line. This has to do with the dotted line growing or shrinking, right? Okay, so you draw your system, you draw your arrows, and then most of the time, at least for this first part of the class, you can start with this first law analysis. So you can go through the derivation that I did, or you can just write out this and write out the assumptions that are underlying in that. And then you should start asking yourself, okay, is there, according to the schematic you wrote, is there any heat crossing the boundary? Okay, now you ask yourself, is there any work crossing the boundary? Or is there any work being done across the boundary? And so then you say, well, how do I know if there's work being done across the boundary? These are the three things that you look for. You don't have to worry about anything else, right? So this is a systematic way to understand if you need to include work in your system or not. Is the dotted line growing or shrinking? Are there wires crossing the boundary, or are there shafts crossing the boundary, right? And that tells you if there's work being done into or by the system, right? Or work being done on or by the system. Okay, and so likewise, I would come here when you're drawing out this, so for a closed system, you don't include MDOT, but for an open system, you do, right? And then you have to always ask yourself, what is SGen? Okay. S.gen. Okay, so we know from here for internally reversible system, S.gen is equal to 0. So how do we know if something is internally reversible? Okay, so this is where you can use this acronym FEDMUCH. So this is friction, electricity through a resistor. This is viscous dissipation, mixing, unrestrained expansion, chemical reactions, and heat transfer through finite temperature difference. Okay, so the ones that you should worry about in this class are electricity through a resistor, unrestrained expansion, and heat transfer through a finite temperature difference. Okay, so the other ones, like we always assume frictionless pistons, right? And we assume frictionless pistons to not have to worry about any entropy generated due to friction. Viscous dissipation. So any fluid has some viscosity to it, right? And now obviously something like air has less viscosity than water, but we have our thermodynamic systems, and you almost always have some sort of fluid flowing through these pipes, right? And so there is entropy generated due to that, because viscous dissipation is just essentially friction with liquids. Mixing, right? So you can imagine you take a tank of oxygen, you take a tank of nitrogen, you open them up into a vacuum, and then all of a sudden you have this cylinder that is mixed oxygen and nitrogen, right? And this is where, Dr. Jones always says, like, can you play the movie backwards in your head, right? And like, does that seem funny, right? So you can imagine the oxygen and the nitrogen separating, going back into their tanks. No, that's not something that will happen, right? So there's tons of entropy generated through mixing, and then unrestrained expansion, right? So that's the actually opening the tank, right? That's unrestrained expansion. That the air or the fluid doesn't just run back into the tank. Chemical reactions, that's pretty straightforward. Heat transfer through a finite temperature difference, right? So you get out your hot chocolate from the microwave. It's at a, I don't know, 60 degrees C, and the air surrounding it is at 25 degrees C. There's some finite difference between the air and the hot chocolate, right? Then I think I may have missed electricity through a resistor. I mean, that one's pretty straightforward. Anytime you have electricity through a resistor, you can't take the heat generated and put it back into the resistor and reverse the change in energy, right? Like, there's tons that is just straight entropy generation. Okay, so let's kind of recap. Okay, so we've gone over our first law, and we have a systematic way Heat and mass are pretty easy, but we now have a systematic way to understand if we have any work interactions in our system. And then if we need to use the second law, we need to determine if it's reversible or not, right? So let me maybe make the distinction. If these happen inside dotted line, then system is not reversible. Okay, sorry, then system is not reversible. Okay, and so this is, you may have heard of externally reversible, internally reversible. So externally reversible is all irreversibilities. So these are irreversible. Wow, can't spell today. Irreversibilities. All irreversibilities happen inside dotted line. Okay. Internally reversible. Happen outside dotted line. And then totally reversible, something like Carnot, right? Is just purely no irreversibilities. Okay, so one question that Dr. Jones likes to ask. Okay, so I mean that is a possible Dr. Jones question, right? For you guys. Is calculate s.gen. Okay, now if I were you, I would connect this to here. Okay, so if he asks this, then let me do this in red. Although I've done a lot in red. Do not choose internally reversible system, right? Because if you choose a reversible system, if you choose an internally reversible system, the definition of an internally reversible system is that s.gen is equal to 0, right? So if you choose an internally reversible system and then you try and calculate s.gen, which should get is 0, and if not, you did something wrong, then that is called a logical fallacy. Dr. Jones, he's pretty fond of this type of question because you assumed that it was internally reversible, and the definition of that is you assumed s.gen was 0 when you drew your dotted line, right? So it doesn't make sense that you assumed s.gen was equal to 0, and then you go through and try and prove that it's equal to 0. No, you already assumed that it was or approximated that it was 0. So please, choose an externally reversible system, which means that all of the electricities and unrestrained expansions and heat transfers happen inside the dotted line. Okay, also unrestrained expansion, that's like tank, but anything with a piston, a piston is always restrained, right? Okay, so we've gone over first law, we've gone over second law, types of work interactions, we've gone over how to determine irreversibilities. So this is how when you're going through your problems, if you have to use the second law, you always need to ask yourself, is my system internally reversible, externally reversible, right? What am I being asked? What can I assume? And this is how you go through s.gen, because s.gen can be confusing. So yeah, I would, at least through these three green highlights, I would definitely write those down, because that's how you determine if your system, if your boundary is internally reversible or externally reversible. Okay. So another thing that I would do is Gibbs. Gibbs isn't a law, but it's the canonical equation, right? So, this is just, this is definitely not refined at all, but it definitely hits all the major concepts, right? And these are derived using the first and second laws, right? So you have TDS is equal to du plus P dV, and TDS is equal to dH minus V dP, right? And so things like this really come in handy because they give you property relationships, right? So these are property relationships, which are really useful because, sometimes, okay, so another Dr. Jones question might be, qualitatively, what does ideal gas constant pressure curve look like on TS diagram? Okay, so this is something else I've noticed that Dr. Jones is a big fan of these types of questions, is how could you prove, you find a graph on the internet, how do you prove if that graph is right or not, right? So what does an ideal gas constant pressure curve look like on a TS diagram? Okay, so this is the main clue, I would say, right here. Right, so it's a TS diagram. So what that tells us is we need T to be some function of S, right? So what you do is, again, start with your basic concepts and fundamental laws, right? So you go through and you might do your first law analysis, right? And you get here and you say, oh, this first law right here, like this does not help me actually, because it doesn't give me temperature as a function of S, right? So then you say, oh, well, the second law has S in it and it has T in it, right? So this gives you a property relationship, but then you might not know Q, right? And as you found in your homework, Gibbs is just a combination of the first and second law, right? So you can use a combination of the first and second law in order to do this, right? So now you look at this and you have T and S. Oh, that is exactly what we want, right? Okay, so let's gonna just draw a line here. Okay, so we know TDS is equal to du plus PdV, or TDS is equal to dH minus VdP. Okay, so which one do we want to use? Right? So this is where you would look back here at your problem statement and you would say, all right, well, what else do I see here that could help me? Okay, well, I know it's a constant pressure line, right? So which one of these would simplify knowing that it's a constant pressure line, right? This would be the best choice because this is going to be equal to 0 now because it's constant pressure, right? So this whole term drops off, right? And you get TdS is equal to dH, which is great because now we can separate and integrate, right? So we can say T is equal, sorry. So here's what I'm going to do. I'm going to say ds is equal to dH over T. And then I know that dH is equal to, sorry, let me just find this definition in the book.